I've been working on several electronics projects in my spare time, and I thought I'd make a YouTube video detailing a few of them. The first project I've been working on is this microcontroller board, which features a Texas Instruments MSP430 microcontroller. I'll talk more about this board in a moment. The next project is this Trackball Module, which has a repurposed BlackBerry smartphone trackball. The next project is this weather module, which features sensors for detecting relative humidity, barometric pressure, and temperature. And last is this GPS receiver module, which features a FastTrack's IT430 GPS receiver based on the Surfstar 4 architecture. Okay, so back to the microcontroller board. Again, this has an MSP430 microcontroller on it. This is from Texas Instruments' latest line of 5 series MSP430s. This is the MSP430 F5510, and it has a built-in full-speed USB interface, which is broken out to this mini USB port here, which is the main sort of data interface to the board and also the source of power. We also have 2 push-button switches, which are just hooked to I/O pins with external interrupts on the microcontroller. And we have a 14-pin JTAG header, which can be used for programming and debugging firmware and such. Beyond the JTAG header, there's also a USB bootloader on this microcontroller, which can be used to reprogram the microcontroller with nothing more than a USB cable. The USB bootloader can be invoked by holding down both push-button switches at the same time. Then we have a coin cell battery holder. This can be used for backup battery power. I'll get into more detail about this feature in a moment. Then we have these expansion headers here. These can be used for adding plug-in modules like these ones, which can add further functionality to the board. And I'll get into more detail about that in a moment. We have a small removable jumper here. This can be used for disconnecting power to the modules and also for easy current measurement. Then we have a small ground tab here, which can be used for connecting the ground lead of an oscilloscope probe or a digital multimeter. And I've also included some branding on the silkscreen layer. This is because perhaps at some point I'll set up a website where I can provide more details about my projects. So far this hasn't happened yet, so don't go looking for it because I haven't really implemented that yet. Okay, so now on to the trackball module. I'm going to talk briefly about some of the design decisions that went into this, and then show a few firmware examples that show off its capabilities. So again, it has a trackball module from a BlackBerry smartphone, and if you're not familiar with how these operate, there's 4 Hall effect sensors located underneath the 4 corners of this that sense directional movement of the trackball up, down, left, or right. And I'm going to quickly illustrate those Hall effect sensors here. Now, in addition to these 4 Hall effect sensors, we also have a push-button switch, which is located underneath the trackball. So when you push on the ball, it depresses a push-button switch. I'll illustrate that here as well. So that's 5 I/O pins that are going to be necessary. The microcontroller is going to have to monitor, and it's going to have to do that either by pulling them. Ordinarily, you would have to do this either by pulling them, which is going to eat up, of course, valuable instruction cycles, and or you'd have to hook these up to like some external interrupt pins so that every time user moves the trackball, an interrupt occurs, and the microcontroller then becomes aware that there's some input going on here. Well, that's quite a few external interrupt pins that would be required. So I thought there was a better way, and I should also mention that there's four different colored LEDs located underneath the trackball as well, which illuminate the ball in one of 4 different colors. And so that would add an additional 4 I/O pins necessary on the microcontroller, which would then give you a total of 9 I/O pins in order to operate this thing, which seemed like a lot. So in order to cut down on the number of I/O pins and make this easier to interface to, I put a serial I/O expander chip on here. And it monitors these inputs and has an output of a I2C serial bus. Now, the inputs here can be monitored simply by reading an input register located in this I/O expander that relates the state of these input pins. Now, to make things even better, this I/O expander has an interrupt output pin. Whenever any one of these inputs changes, this interrupt output pulses low. So now your microcontroller can sit in sleep mode or be off doing other tasks, and when an interrupt occurs here, it can simply jump to a interrupt subroutine and read the input register on this I/O expander and determine the state of these inputs and figure out what has changed. Okay, so now I've programmed the microcontroller board to show off some of the features of this trackball module, and simply plugs into these expansion headers. But before I do, I just want to demonstrate and talk about the horizontal spacing of these headers are such that they will easily plug into a prototype board such as this one, or an Arduino Shield, or any sort of other prototype board with standard hole spacings. They'll even plug into a solderless breadboard like this, with room to spare on either side for additional wires. So these are designed to be easily added to any to other projects, and they're designed to be fairly general purpose. So anyway, back to the demonstration. Plug this in. I'm going to apply power to the board through the USB cable, and I notice that the LED has come on. I'm just going to dim the lights. And if I scroll this trackball to the right, you'll notice that the LED color has changed to white. If I scroll it to the left, it turns blue. If I scroll up, it turns green. Scroll down, it turns red. So the firmware detects the motion of the direction of rotation of the trackball and changes the LED accordingly. It's a pretty sensitive trackball. Sometimes the light even changes just by jiggling it. If I push the center button, the LEDs will turn off. Move it again, they turn on. Perhaps a more useful example of the trackball module is one which can actually operate as a computer mouse. This demonstrates the usefulness of the USB interface on the microcontroller. The microcontroller has been programmed with a Human Interface Device, or HID, USB profile, which is what most computer mice and other input devices use. And if I plug it into my USB port on my laptop, which is what we're looking at right now, the screen of, with the Windows automatically installs the driver in the background, and now this is a Windows computer mouse. If I scroll around with the trackball, hopefully you can see the cursor moving across the screen. If I click the trackball button, that actually serves as a left click. So I can do things like open folders with a double click. If a left click also turns the trackball red, if you notice. These buttons over here also serve as mouse buttons. So this top button again is a duplicate left mouse click. The bottom button is a right mouse click. A right mouse click turns the trackball button blue. But yeah, this essentially implements all the features of a standard Windows mouse. Okay, next I want to talk about the weather sensor board. I'm going to go into a few of the design decisions behind it and then demonstrate some firmware examples. So this has a pressure sensor, a barometric pressure sensor from Bosch Sensor Tech. It's called the BMP-085. And this device has an I2C output. There's also a relative humidity sensor from Honeywell. It's the HIH5030. This device has an analog output. Now, what I've done is added a 10-bit A to D converter here. It's single channel. And this A to D has a I2C output as well. These two I2C buses are connected. So both sensors can be accessed over the same I2C bus. Okay, so now that we've talked a bit about the design of the weather module, I'm going to plug it into the microcontroller board, and I'll show you a firmware example of it operating. I've reprogrammed the microcontroller with driver software and so on for these different sensors, and also it's been programmed with CDC or communications device class, USB class, which is going to set up a virtual COM port on my laptop. And I'm going to plug this board into the USB port. Now, one thing you'll notice is that there's a green flashing LED here. The main loop in the firmware executes once every second, and every time the main loop executes, it toggles the LED, and that's just to give you an indication that everything's running smoothly. Now, I've written a C# application. So what I'm going to do is select COM8, which is the virtual COM port that's been set up, and hit connect. And the values from the humidity and pressure sensor are being displayed now. The pressure sensor also has a built-in temperature sensor as well. So you can see that the temperature in the room right now is about 75.4 degrees Fahrenheit. The pressure is about 99.4 kilopascals. The relative humidity is 38%. And the altitude, calculated using the International Barometric Formula, is about 159-160 meters. What I can do is breathe on these sensors, and you can watch the values change. They're quite sensitive. Alright, so now the temperature shot up to about 80 degrees there for a moment. The pressure increased too. The relative humidity increased quite a bit as well. Yeah, these sensors are quite quick to react. I'll breathe on it again. And that's an example of the weather module in operation. Okay, the last project is this GPS module. Again, it's based on the Fastrack's IT430 GPS receiver, and this in turn is based on the Surfstar 4 architecture. It has a number of features for low power operation, which makes it great for battery operated applications. These Surfstar 4 devices are generally designed to operate at 1.8 volts, as this one is, but this whole module here actually operates at 3.3 volts. There is a 1.8 volt voltage regulator which supplies the 1.8 volts to this chip. And there are also level converters on the output pins, and the input pins are 3.3 volt tolerant. There's an SMA connector up here for connecting a active antenna. I'll be using this small patch antenna, and there is also a green LED located here, which blinks green at 1 pulse per second when an active position fix is obtained. Okay, we're here at Cornell University campus to demonstrate how the FastTrack's IT430 GPS module works. I'm going to plug it into my laptop and we'll see what happens. Okay, so when the IT430 first boots up, it boots up into a low power hibernate mode. And in order to get it out of hibernate mode, you push this button here. A green LED comes on to indicate that the FastTrack's module is now in full power mode and ready to acquire a position. Okay, now I'm going to start up the FastTrack's GPS Workbench software. This is software that shows all the settings and configuration of the FastTrack's GPS module. And this module acts a lot like the weather module in that it relays all its information to the USB port and is configured as a virtual COM port. So we need to enter COM8 and in this case and a speed of 57,600 and click OK. And now I'm taking the device out of hibernate state, and there it goes. Okay, so now we're starting to see NMEA strings scrolling up the bottom of the screen, and you can see we're already tracking 6 satellites, and we should be getting a position fix shortly. This will be a cold fix since the coin cell battery was not in the coin cell holder on the microcontroller board, so this will take a little longer than it would have if we had the battery backed ephemeris data saved in the FastTrack's unit. But okay, now we have a position fix. You can see our latitude, longitude, altitude, and speed, and heading, and so on, listing there down at the bottom, and some of the bar graphs there indicating the satellite numbers have turned blue, indicating that they are satellites that are currently being used for our position fix. And so yeah, this gives you an idea of how long it takes to get a cold fix when you have a clear view of the sky. Okay, now I'm going to demonstrate how to track your position on Google Earth using a program called Goups, which is made by a company called Goups Technologies. There's a free version available, and what this is going to do is act as sort of a go-between between the GPS module and Google Earth. And so what I did there on the configuration screen is typed in the virtual COM port parameters, and now it's loading our position in Google Earth and zooming in on our location. So there's the upstate New York area, the Finger Lakes area, Ithaca, and Cornell University. And there is our position right there. We are not moving right now, but if we were, you'd notice that our position would change along with our movement. This position is updated at regular intervals, and also you'd notice that a line will be drawn out at our past positions to indicate the path that we've taken. Okay, so I hope you liked this video. If you did, please click the like button and leave a comment. Thanks for watching.